All right, welcome to permutations, combinations, and the binomial theorem. So that's chapter 11. So with that, we're going to start with permutations. So that's section 11.1. And we're going to go back to something you already know, which is opening your locker. So your combination lock. Well, how many combinations are possible on your lock? And how would you figure that out? Well, go look in your combination lock. How many different digits are there on there? Some of them varying amounts depending which one you have. I think normal is 60, and usually we do that 3 times. So you have a choice of 60, choice of 60, and choice of 60. So now that we know how many times we're picking it and how many choices we have each time, well, what's the total? Well, you'd multiply these all together. So 60 times 60 times 60. And you'd end up with a total of 216,000. So that's a lot of combinations. And that's why we think they're sort of secure. Now, some of you might argue like, oh, is that last one really true? There's ways around this. Yes, but mathematically, there's 216,000. I know as your locks get older, sometimes one off, one or two off, doesn't matter. But we're not worried about that. Now, if I use the same numbers, but in a different order, would the lock open? So, for instance, like if my combination was 10, 15, 20, could I go and put in 20, 15, 10? Well, no, that wouldn't make sense, right? Like it has to be in the right order with the right numbers. Well, mathematicians would actually say you don't have a combination lock, you actually have a permutation lock. And permutations care about the order. So we have this definition and any of the ways we can arrange things where the order is important. Now, sometimes repetition is allowed, sometimes it's not. It depends on the question. And what it means by repetition is like our combination lock. We're allowed to actually have the digits 15, 15, 15. So we could use the same number over and over again. Sometimes that's not allowed. Honestly, I've never seen a lock where all 3 digits are the same. So I'm thinking the manufacturer actually probably doesn't allow that. So then maybe really with that first lock choice, yeah, you have all 60 choices, but I'm guessing the manufacturer doesn't allow the next one to be the same number. So you only have 59 choices the next time. And then for the third one, well, now there's 2 choices that can't be. It also seems, and this is maybe not true, but it does seem like the choices are rarely close to each other, like one off or something. They're usually kind of spread out. But that could be completely wrong. It's just kind of what I've noticed. Let's move away from the combination lock example though. So we have 9 switches on a fuse box. How many different arrangements are there? So in a fuse, you have an option. It's either on or off. So if we look at switch 1, there's 2 choices. Okay, so it could be on or off. For switch 2, it's the same thing. 2 choices. And I'll just make lines to represent each fuse. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. So for each fuse, we need to decide how many choices are there. Okay, well, for each fuse, there's 2. Now to figure out how many combinations or permutations there are of these, then we need to multiply these all together. And that's called the fundamental counting principle. So if I see here, I've got 2 to the power of 9, as this can be rewritten as, which is actually 512. Now it might be easier to look at why that's true if we just look at the first 2 fuses right here. So fuse 1, it can either be on or it could be off. Now for fuse 2, if the first fuse is on, the second fuse could either be off or it could be on. And then in the situation where the first fuse is off, again, the second fuse could either be off or on. Now we want to see how many different possibilities there are. Well, we have 1 and then 2, so there's 2 possibilities there, and then 1, 2. So in total, we have 4 possibilities if we had 2 fuses. Well, if we just go 2 times 2, which is the number of choices for the first one, times the number of choices for the second one, then you get 4. And if we go to the third one, each of these would be branching off again into 2, which is why we're going to multiply it by 2. Like this would be on, off, and this also would be on, off, if that was the variation we were looking at. And you can see we're actually doubling it from each one. Now, for some reason, maybe you've got some weird fuse, or it's kind of halfway, meaning it's been activated. Then maybe you have a third choice for the third one. And now you can see each of these branches would turn into 3 times more. And so you multiply by 3 then. Let's take a look at letter B then. So how many 3-letter words can be created if repetitions are allowed? So we've got 1, 2, 3 letters. There's 26 letters in the alphabet. So we've got 26 letters as our first choice. It says repetitions are allowed. So that means we're allowed to use the same letter again. So I've still got 26 letters for the second choice. Third choice, same thing. So we're going to use the fundamental counting principle. So it's going to be 26 times 26 times 26, which gets you 17,576 different permutations of this. C is our last one. How many 3-digit numbers can be formed? So 0 can't be the first digit though. So again, all 1, 2, 3 digits. Now, normally there's 10 different options, but because 0 can't be the first digit, I've actually only got 9 choices for that first digit. Second digit, we go back to 10, and third digit, we also go back to 10. So then when we multiply those using the fundamental counting principle, we get 900 different permutations of this. Our definition for fundamental counting principle is this. So FCP says that if one task can be performed in A ways and a second task can be performed in B ways, then the 2 tasks can be performed in A times B ways. And we'll look at this one more time. So a store manager has selected 4 possible applicants for 2 different positions at a department store. In how many ways can the manager fill positions? All right, well, we've got 2 positions. So position 1, position 2. For my first position, I've got 4 possible applicants. Now, that same applicant, whoever gets chosen in the first one, can't be in the second one. So then we only have 3 choices. So it's going to be 4 times 3. And so we get 12 different ways that we could fill these positions. Now, B gets a little bit trickier. In how many ways can a teacher seat 4 girls and 3 boys in a row of 7 seats if a boy must be seated at the end of each row? Now this is where these questions get a bit trickier. We have this restriction, a boy must be seated at the end of each row. So my first thought is, well, how many seats do we have? We have 7. So let's write those out. So 1, 2, 3, 4, 5, 6, 7. It's easier to do the restrictions first. So this must be a boy and this must be a boy. Now, how many boys are there? Well, there's only 3. So then, if I go here, well, I only have 3 possibilities. And then for the second position, well, one of the boys is already in the first seat. So we have 1 less boy to pick from, so there's only 2 boys left. Now, there is 1 boy left over that isn't on either of the ends, which means he's going to get added to this total of 5 or 4 girls. So we have 5 people to choose from now for the rest of these seats. So it's going to be 5, 4, 3, 2, 1 as we position each person. And now we just use the fundamental counting principle and multiply. So equals 720. Now this does bother me a little bit here. So this 5 times 4 times 3 times 2 times 1 seems like it's going to take a long time to write all of that out. There's got to be a faster way. Especially, can you imagine if we had like 20 people and you had to go 20 times 19 times 18? Oh, and there is. So this can be written as 5 times 4 times 3 times 2 times 1 is actually 5 factorial, or 5 exclamation mark. And we're going to look more at that in the next video.